Hello friends, this is Partho sir. Very good morning. In the last few classes, we have discussed the problem based on electromagnetism, current, electricity, capacitance and electric field. We have also discussed the problem based on the pulley and spring associated with the simple harmonic motions. As for the recent trend of the IIT Advance, NEET as well as JEE Main, we have seen that there are some problems which are coming from the fluid mechanics area. So today's problem is basically based on the Bernoulli's theorem, which is an integral part of fluid mechanics. Now let's see what the problem is. It is mentioned over here that water is filled in a uniform container of cross-sectional area A. It shows that means this is, suppose it is a vessel, and this particular vessel is full of water, and the cross-sectional of the vessel is uniform, and that is A. A hole of cross-sectional area small a is placed at a certain distance below the surface of water. That means, suppose this is the portion where hole is made, and the cross-sectional area of the hole is small a, and it is done over a distance, below a distance y from the surface of the water. So this is the position of the hole, and this is the position of the surface of the water inside the container. Now what is mentioned, that water streams out and hits a small block on the surface at some distance from the container. That means from this particular portion with a certain velocity small v, the water is coming out and it hits a block which is placed at a distance x from the base of the container. Now you have to find out, now this particular block is moving along the surface once the water is hitting. Now we have to find out what is the initial velocity of the block. What is the initial velocity of the block, so that the block is moved on the surface in such a way that stream always hits the block. So we have to find out first the initial velocity of the block. Now let's first, what we will do, we will use the Bernoulli's equation for this particular point and for this particular 2 points. Now in that particular point we know very well that suppose capital V is the velocity of the liquid which is flowing vertically downward direction inside the container. So in that particular point the pressure energy head, that definitely pressure energy will be P0, and here also we have seen the pressure energy head will be P0. So in that particular point the three energy constants, three energy head will be P0, that is half into rho into capital V square, and here the potential energy, because it is certain height from that particular point, so it will be rho into G into Y. So this is the total pressure energy, total energy, that is pressure energy head, kinetic energy head, potential energy head at that particular point. And if we equate this with the total energy head at this point, then we will get that is the pressure energy head, and half into rho into small v square, that is the velocity of efflux, and also the potential energy head here will be 0. So this 2 will be strike out, and if we just take it over here, so you will get root over gy is equal to half into rho, so it comes down to small v square minus capital V square. And if we take it as a common, that means small v square, if we just take it as a common, so we will get 1 minus capital V square by small v square. Now here that equal to rho gy, so we will get ultimately 2 rho gy by rho is equal to small v square into 1 minus small v square by capital V square. Now here it has been mentioned that capital V, here if you see from the equation of continuity, that capital V will be much lesser than small v. That means capital V will be much lesser than small v. Why it is so? The reason is, here the cross-sectional area small a is much lesser than the cross-sectional area of the container where the water is residing. So naturally this portion we can neglect. So if we strike it down, we will get the velocity of a flux, that is the velocity of a flux, and that will be equal to root over of 2gy, and that will be our first equation, that is the velocity of a flux. Now what we have to find out, the velocity of the block. Now before understanding what will be the velocity of the block in the horizontal direction over the surface, first we have to use the formula of a range. That means range is equal to, we know x is equal to, that is the velocity of a flux, that multiplied by the time taken by the block. So here we will see that velocity of a flux, that will be already we have got it, that is the velocity of a flux will be that will be multiplied by this, that is this range will be, that x is equal to the range. So range will be root over of 2gy into root over of 2h by g. Now why it is 2h by g, and which one is h? Now this distance first we are considering as h, which is equal to 20 meter. So for the sake of this problem, first we are considering it as h, and once the problem will get finished, we will put the value of h if it resides. So this is the range. So what we will do, if you have to find out the velocity of this small block in the horizontal directions, then we have to differentiate it with respect to t. So we will get, after differentiation, dx dt. So we have to differentiate this entire things. Now this is a constant, this is also a constant, so you can strike it down g and g over here. So ultimately you will get, after the differentiation of this entire things, so you will get 1 by 2 into root y into dy by dt, and here it will be root over 2g into root over of 2h by g. So just what you will do, you just simply started to strike it out, all this portion. Here it is 2, that's root 2 root 2, you have to strike it out. So you will get root h by root y into dy dt. So what ultimately this equation stands for? Now this equation stands for, this equation number 2. This equation number 2 basically denotes the velocity of the block along the x-axis or along the horizontal directions. Now as for the equation of continuity, from equation of continuity, we can say that A, that is the cross-sectional area of this, into V, that is the velocity of the liquid or water which is moving in the vertical direction, is equal to cross-sectional area of the whole, that is small a, into what is, that is the velocity of a flux, that is small v. So this is capital V and this is small v. This is the velocity of the liquid which is moving vertically in the downward direction, and this small v is the velocity of a flux which is moving into the right hand side in horizontal direction. So what we will do here, we will just simply put the value of a flux, that is a into small v, that means root over 2gy. We have got this value of a flux, that is this, from the value which you have already got over here. That is in the first equation we have find out the velocity of a flux, that is the velocity of a flux we have already find out. So what we'll do, we will just put this value of the velocity of a flux over here. Now what we have to do, now simply just check what we will do. We are simply using the value over here, that means the value of v, that is our value will be this value. Now how we are going to solve this problem? So that is the velocity of the block, that means this particular velocity, that is dx dt, which is the velocity of the block, and that will be equal to, what is the value, that is root over h by y. So we can say root over h by y into dy dt. Now here the issue is this velocity is nothing but dy dt. So we can say these things, that dy dt is equal to a into root over 2gy by capital A. Now this value, ultimately what we have to do, we have to place this particular value. Now where we will place this value? Now this particular value we are going to place over here, that is in that particular equation, the equation which we have got over here, root over h by y into dy dt, that particular value we have placed over here, that is in that particular place. So we are going to get a into root over 2gy and by capital A. So here you will see that y and y will be strike out, and in that particular case it will be root over a small a by capital A. This will be one portion, and another portion will be root over 2gh. So this will be the portion. So now the value of small a by capital A, which is already mentioned over here, that is 1 by 20, and root over 2gh, which is also given here in that particular problem, that is our h, because this particular and we are going to get, that is ultimately it comes down to root over 2gh. So what we'll do, that we will just simply place the value root over 2gh, so that value will be the 20. So in the block we can mention over here, that is root over 20, that value we are just placed over here. So if we just place this particular value over here and strike it down, we will get 1 meter per second. So what are the things we have done in that particular problem? So if you just see, then you will able to understand that how we have solved this particular problems of Bernoulli's equations. So this is all about that. First we have used the Bernoulli's equations for that particular point, and these 2 points we have estimated all the energy head, that is first thing the pressure energy head, kinetic energy head, potential energy head, and also we have find out in that particular point all the energy head like pressure energy head, kinetic energy head and potential energy head. And now from this we have find out the velocity of a flux, that is root over 2gy. Now then we have gone to the range, that is how far the block is presently moving or presently stands, that is x is equal to v into t. So on that basis we have just mentioned x, that is root over 2gy, that is the velocity of a flux, and multiplied by time, that is root over 2h by g, and h is the height, that is 20 meter, that is root over 2h by g. So then we have differentiated this entire portion, this portion we have differentiated with respect to t, and ultimately we have got a value, that is root over h by root over y into dy dt. Now from the equation of continuity we can say that capital A into capital V, that is area into capital V, is equal to small a into v. So that v is basically the value of dy dt. So what we did, we have just simply find out the value of dy dt by using the equation of continuity, and after getting the value of dy dt, what we did, we are just simply follow and put it over here, and that's the way we basically solve this particular problem. So thank you very much for your patient listening, and if you really like this particular video, so please do share and subscribe so that you can get all my other videos. Thank you very much.